So I'll leave the who am I, do the obligatory, we're not announcing anything product, and don't take away that VMware is going to announce, usual caveats. I'll also walk through a few obligatory upfront trend slide. I think many of people have already talked about it, so be patient. We may have seen it, it's obvious to you, but maybe a couple of different points I might highlight just to set the context a little bit here. Obviously, data growth is going on. Compute needs are accelerating. The middle chart is kind of interesting. Is my life, I used to be, for a long time, at Sun, and we used to sell memory as a currency. If you go back in the 20, 30 years back, memory was a currency we used to optimize for building big memory machines and et cetera. And I actually tried to start a company in distributed shared memory in 2003. At that time, I thought that's a way to do it. But Moore's law was still ahead at that time, that you could not bet against memory, where you can just ride the curve. And what's changed 20 years later is exactly the curves. I think Chris showed and others showed that it's not the case anymore, along with use cases and the needs. Couple of different ways to look at the trends, and where I want to zoom into the problem space a little bit more. Obviously, the rate of growth of network versus storage bandwidth versus memory bandwidth has been plateauing. There's another view of the same thing. These are borrowed charts from Google and the internet. So I'll go through, sorry. And we have had a plethora of technologies to support for different memories. And these are 10-year, $10 billion bets, as we have seen with Intel, with DCPM, with their 3D XPoint. And any new technology is not easy to come by, but still there is a huge need for something to sit in between. One way to think about very simply is where we are today, a system, just take a generic x86 and maybe some ARM CPUs as well. There is at least 2 types of memory today and mainstream x86 from some. And obviously it's going to CXL and some speeds and feeds there. But the interesting point is the emergence of CXL is going to bifurcate and be able to use increased bandwidth, disaggregate, do hot plug, and all the points that is made. And it also is going to drive a chasm between the memory and storage. So one way to view the latency bandwidth cost trade-off, and I try to put it in a simple chart to summarize all of that. So on the y-axis, as you've seen, it's about the latency, and the x-axis is about bandwidth. And we cross 250 and north of that with the multiple channels with DRAM bandwidth. And as you go to other technologies, you get a big drop in the bandwidth. But there are 2 interesting lines there, the RDMA barrier and the sync barrier, in the sense of from a programming model. One way to think about it is the industry has understood over 20 years how to deal with 1, 2, 3 NUMA hops from a programming model and a performance model. And that's sort of been, if you look at the HPC era from way back when, the 1 microsecond was an interesting number. People build SMP, coherent interconnects, et cetera. That's the number that seems to be meeting the performance number. For certain other classes of applications and programming model, I think the RDMA barrier is another one. So the 1 microsecond is mnemonically a way to think about, and the 10 microsecond is another number. Anything beyond that, the memory model starts to fall apart. But even beyond 1 microsecond, the memory model is a little bit difficult to meet the performance. There's always a trade-off, performance cost and reliability. So try to put that in a simple chart to convey the point. So what does this all mean in terms of delivering building systems and end users having value extracted from it? There are 4 dimensions. One is obviously always is TCO and power. The second is simplify the complex memory hierarchy that's emerging. There is an emerging chasm, which was not, it has been there between storage versus memory, but how do you bridge the gap? Because storage inherently is at scale and resilient, and memory was bound and asynchronous, so that has to be addressed. Doesn't mean one crosses over the other, but you got to have elements of one cross over to the other, and most important is resiliency model. A simple way to look at all of these are, we get fairly good capacity at the register rate of even the existing Moore's law at this is OCP, and I've taken some open 19 form factors here for different reasons, but it can be applied to OCP as well, that you can get to a small radix cluster, an 8-node cluster or 4-node cluster to get enough capacity in memory. That's the point to highlight here. And a single rack will have enough capacity for memory model. That's starting to emerge down the decade. I think we touched upon the storage versus memory. There's a cost trade-off. I like the way Chris defined. I'm going to hijack and use the latency, the bandwidth tier and the capacity tier. I'm going to add 2 more tiers. I'm thinking on the fly, and maybe there's a way to collaborate. Is a latency tier and a cost tier. The cost could be flash at some level you can think of, and the latency tier will always be some form of a DRAM solution tied to the processor. So maybe there are going to be 4 tiers, and that's a very good characterization. I would love to use that. But I think the important part to understand is the memory-centric view and the storage-centric view of the world. I've been at this nut for about 20 years, and really the big issues of usage of memory is always bound with compute. And if you bound with compute, how do you solve the programming model? It all gets intertwined. I think we're finally getting to the point with CXL as a great enabler to unwind a little bit with the coherence model that's built in to simplify the programming model. But you still have to address the failure or resiliency mode that has been built in the storage paradigm forever, and the programming model of synchronous, asynchronous, and a whole bunch of other things. And how do you deal with? So these are the important consideration in building systems at scale. There's another thing that I want to highlight is what's good for the goose is not necessarily for the gander, in the sense that we all look at what the hyperscalers do and build systems at scale. Having one big flat network simplifies the programming model. But the world is not just that. The world is many ways and is getting even more bifurcated and trifurcated and multifold with edge, quote unquote, edge and other things. But just to give you an analogy, Hadoop was the great savior to do big data. Guess what? That was not really the way it permeated everywhere in the enterprise SaaS. It was good for the consumer SaaS at scale when you have petabytes going to zettabytes, but not necessarily. Databricks did a better job and solved the problem for a class of users at certain limited capacity. The same thing will hold in the memory paradigm as well. As you will need large distributed memory systems for a class of use cases, maybe in the consumer SaaS, but there will be a whole class of other users that will be limited capacity and still want to be able to leverage it. And there's a different cost, performance, capacity, resiliency model trade-off. So the 3 things that I really care about is TCO, scale, and resiliency at the end of the day, if you will. So this is the basis in which we started thinking about what to do under Project Capitola to both bridge the divide between the existing storage and memory paradigm and provide software-defined memory, as Manoj would like to call it, and everybody else calls it. And the core elements of that is we'll do it in multiple phases. The first phase is start with local tiering with cluster support. So we think of it's not just the tiering, it's how do you also schedule a particular workload or a VM based on resources that are available. So memory becomes a tiered resource as well as a scheduling resource based on the cluster level placement problem you can have. Again, that problem is different where VMware is playing into than a Facebook or a Google may face. Now, there may be common things when you have many workloads going into the cloud too, but there are similar but different. Just keep in mind. The second phase we'll do is cluster-wide pooling. I think this was talked about and announced at VMware just a month back, and you'll see more of it coming in the next year or 2 from VMware. To reinforce the point I mentioned earlier, it's all about scale, TCO, and resiliency. The things that we put to play are fabric attached, leverage NVMe for the scale and capacity side, including and other CXL-based attached devices, Intel Optane, get to pooling eventually. And how do you deal with resiliency is do active and proactive monitoring and remediation based on failure modes. So it's important to track and do. Memory is the kernels just panic for every small issue with memory. So you have to be careful how you're dealing with memory modes and resiliency modes there. So Project Capitola enables transparent tiering. Initially, it starts with 2, as what Chris said. It'll go to multiple tiers. Let me just back a little bit, sorry. There'll be unmappable page devices, which is obviously the existing locally attached NVMe devices, as well as pooled DRAM perhaps even, but unmappable byte-reversible devices. Both will be supported under the Project Capitola, which is part of the ESXi kernel roadmap story. And it'll be done along the lines of looking at cost, where we promote cheaper tiers first to manage the cost, subject to the bandwidth and the performance constraint that exist, and the utilization, or rather the bin packing that happens in a particular node and cluster, and move things around based on that. We'll extend up to 3 active tiers. We try to minimize the performance without disruption. That's the key end customer goal. And integrate the tiers in a very modular form. There are a lot more details behind each one of those bullets. I'm just abstracting at a high level. In very simple visual form, it ends up being 3 tiers of management. One is cluster-wide, node, and tiers. So think of any page can be managed at all 3 levels based on what function, what optimization you end up doing. Okay. This would be the eventual roadmap that we will craft over the next few years. DRS, which is the distributed resource scheduler that does cluster-wide management. The host monitor and the ESXi kernel will do at node level, and then the VM monitor will be involved in the memory management, page management, infrastructure, and all of them will coordinate between each other and do the resource management and pooling. Let me go into a couple of details. We are still in the process of doing a number of benchmarking and data that we have published and shared, and it'll continue to work. One is taking HammerDB, I think that was referenced earlier, and looking at what are the configuration we set up. But the key idea, as you would expect, is the red line marks the performance for as is without tiering enabled. And obviously, it goes down when you increase the actual working set to a larger working set over time. And with the tiering enabled, it improves the roof line, if you will, or the top line. It's not the ideal point. It's still pretty good, and you get significant cost savings. In this case, you think of cost or performance based on capacity. That's a way to look at the world. But the important element of that is, do we conserve bandwidth along the way when you do the tiering? The lower is better. So the red line where you had drop in performance with the capacity, it was actually trying to consume more. It was a brute force approach, as you would imagine, in the existing systems. Now being smarter about it actually conserves bandwidth and delivers you better performance, which is the place you want to be. That was HammerDB. Think of as a canonical database, not necessarily all databases, but a representative of many databases. And this is another set on SpecJBV, which is a canonical app tier benchmark. Similar characteristics. You get an improvement with the tiering where we are, and expect these algorithms to continue to improve over time. We are not static, but this is where we are at a point in time. Same thesis and the same conservation or improvement in bandwidth as the capacity increase. So with that, let me get to the quiz question that who knows ATM? I think what Manoj asked, his interview question is, if you are young or old, I know. What does ATM mean to you? I know. What does ATM mean to most people? I guess the point of his question was, there was a huge debate and hotly debated back in the 90s about ATM versus Ethernet. If you look at all the interconnects that existed, and there was the elegance of ATM and all the resiliency and all the other aspects of it, and then here came along Ethernet, that truck went moving, and then got the economic value and the ecosystem value and railroaded everything else over time. And that was an interesting thing that happened. That's an analogy I'm going back in history to see where we are, is because every time this concept comes about memory and storage, there's always this debate in the last 20 years is, all I've got is Ethernet. No, nothing can touch Ethernet. Nothing can replace it. The game is over, so don't bring anything else. I think for the first time in 20, 25 years, we are seeing that CXL is going to give a challenge to Ethernet as is for a certain class of use cases. And the 3 elements that really make it different is the coherency, the programming model, and a couple of other things. I think the coherence model is a big difference that I don't think it makes sense. It'll violate any Ethernet and IP principles if you do that. So the question is there value in the coherence model? And I think it's going to be driven by, again, as what everybody said, is the marriage between compute and memory is an important dynamic. Having a coherent accelerator in the memory part simplifies the programming model fundamentally. Although graphics has played around with PCI forever, I came from a school of having done RISC microprocessors. I was lucky to be part of Sun doing ILPs. Then I led the whole charge doing thread-level parallelism, doing multi-core. And way back in my 2003, I said it was all memory-level parallelism and data flow was my thesis. It was 15 years too soon. But I think it's coming now of the confluence of the interconnect, sort of media technologies. I wish Intel could be more successful and others can be more successful with 3D XPoint and other media. So we still have a gap in the media side. Hopefully the industry, Samsungs and Microns can solve it. But the use case, which is the programming model and the accelerators are coming to play, that is driving the need that is different than the last 15, 20 years. And sometimes the law of unintended consequences, a dumb thing like a CXL DRAM may be the one that's going to shape and reshape this whole curve. It's very hard to put an Ethernet and a DRAM together and make it all work with a performance model. So the debate that was ended 25 years may restart in the next 15, 10 years, and let's see what happens. So with that, let me close. There's a company called Fungible Computer, but I think we are going to rethink and reimagine at some small radix, maybe at a rack or a cluster level, a small cluster, what is a fungible computer in the sense that you have flexible set of resources and the software layers will start aggregating it and create dynamic pools of within, again, the coherence domain, the performance domain, and the latency domain, and what are the use cases? There will be a whole bunch of use cases which are applications that demand the latency, and we'll figure out. Software will change like happened. We went from big SMPs to massive scale out with Ethernet. There was a price performance equation that crossed over between 95 and 2000. The same thing, the software guy said, I don't want to write into a scale out distributed nodes in 1995. I like SMP, it was easy to write to. We'll have the same flip in the next 5 years, that certain class of applications, the price performance will be different. People will write to that, and you'll have a bifurcated model. So that's my end. Thank you. I guess I timed it well.